Hello, today I would like to introduce some elements of matrix calculus. It's actually very easy and straightforward, so I hope after some thinking you will have the same opinion. Well, I'd like to start with this picture which introduces the second chapter, and that's actually something we are after, right? Doing data analysis is based on percepting a lot of data, do something with them, and try to store them in a more reasonable and more understandable way. And whatever we are doing usually is based on some sorting, filtering, and on the way we shall need the matrices. So what are the matrices? Matrix is a scheme which you definitely have seen already, not only in the last 2 weeks, but whenever we are dealing with some equations, right? So linear equations. So you have something like 2x plus 3y equals, say, 0, and then another one would be, say, 1x plus 1y equals, say, minus 3, right? And if you want to solve that's something definitely everyone could do. You compute x from one of them, and then you put it in, you substitute into the other, and you have one linear equation, and there you can compute, because if you have only one equation, so it would be something like 2x equals 7, then we immediately see that x equals 7/2, right? And of course, it's now a question which scalars we are working with, because if we want to see only integral results, then the solution would have the equation would have a solution. If we work only a field of scalars, or at least a ring where you have the division, then it works, right? So you can see what it would be if we, for example, we're doing it in the remainder classes. If it was Z3, it would be a different result. If it was Z7, it would be 0, right? So that's easy. So how does it link to matrices? Matrix is a scheme which would just allow us to write the same set of equations in such a way that you have just the coefficients in the array, 2 by 2 array, and we write x and y here, and we know that there is the multiplication, and the multiplication works in such a way that you take the row in the left item and a column in the right item, and that will be the first thing in the result here, right? So in our case 0. And then you take the second row and the second again the first column, and you will get the second thing. So here it will be 0 and minus 3, right? And now the question is whether we can compute with that in an easy way. And the answer is yes, we can, because if we go a little bit further here in the text, so you will see that the basic thing we want to handle here are the vectors. That's what we had here in the other column here on my screen. That was the columns in the matrix, or the column x, y, or the result 0, minus 3. And the vectors are for us, for now, n tuples of scalars. And the matrix can be understood in such a way that you simply take an A, that's the matrix. You take x, some other. So you take, I will write it this way. So small, but say v. This is the vector v, and it equals some other vector, say w. This is w, right? And we compute it the same way as we did before. And now the question is whether we can always compute the solution for the v whenever we get the w. And so we would like to do it the same way as here, because here we simply computed the inverse of 2 and multiplied with the inverse. So here we multiplied by 1/2, and this is how we got the solution. And we want to do the same thing here with the matrices. So how can we do it here? So we would like to have another matrix which would have the property that if we multiply with the matrix, I will call it also A minus 1 times A, this should be the unit matrix. So the 1 and 1 on diagonals and 0 elsewhere, and this will be then A times V, and this will be A minus 1 times W, right? So as soon as we know this matrix, we simply compute the V, because E times V will be V, by this simple manipulation, right? And one of the goals of the next pages is to learn how to do this computation and how to decide about the existence of the inverse for general scalars. Right, so let's have a look how to go there. So first of all, we introduce some conventions, right? So in the text, that's just coming back to the guidelines, what you perhaps will read. For those who want to read better the practical column, it doesn't matter, so you don't have to follow everything I'm talking about here, but at least the conventions are good to know. So the vectors will be, as I already told, for us will be just n-tuples of scalars, and the n-tuples, because they are scalars, so we can sum them component-wise, and we can multiply each of the components separately with another scalar. So these are the two operations. And you can remember that in the plane, this was exactly what corresponded to the standard operations with the vectors as the arrows in the plane. So you can imagine the same for the plane, for the space, but the main point is that, and that's the core of mathematical thinking, that you can imagine how it works in the plane, but at the same time you carefully concern about whether the arguments you use are general, so whether the same thing will work for every n. And that's the basics of the matrix calculus, right? So we say that the vectors are simply elements in the n, so n-tuples of scalars. We define how they are added, and we know that they will always have all the rules of the commutative group with respect to addition, because they've got it component-wise, so that's okay. And we get immediately from the definition that there are these distributivity laws and also the associativity with respect to the scalar multiplication. And the last one is sort of more ridiculous, so it's not so completely clear why exactly this, but this is not too difficult, and it will be clear later why we need that 1 times v is v. Here is all obvious, yeah, from the definition. So these will be the four properties we shall use in our argumentation in the text, and therefore whatever object fulfilling these 4 properties would also share all the results, right? And now we come to the matrix. So matrix is an array which has got m rows and n columns. And with the matrices, again, it's actually vectors of size m times n, right? So we can just read the matrix row by row and consider it as a long vector. But we rather will take care of the shape, and we talk about the rows, the columns of the matrices, as I did in the simplest case, and we always get the additive inverse, so that's this one, and we always have the zero matrix there. So you see it's so the formulae just tell us that it's again a vector space in the same sense, right? So it satisfies all the things. But now we are coming back to the understanding of matrices as equations, and that's here. So each matrix can be understood as coefficients in a system of equations. And if we define what the matrix multiplication is, exactly as I already indicated it, then we can write the very system in the matrix symbolics this way. So it will be A times U equals W, right? Or I had B there. So this will be our way of understanding and writing equations all the time. And this brings us also to the definition of the product as I introduced it. So here it's formally given, and this is the unit matrix, and here are the propositions, right? That actually, if we deal with, say, square matrices, so we always, if we deal with two matrices, then the only thing to remember is that we can multiply them only in such a case when the size of the number of columns of the first matrix is the same as the number of rows of the other matrix, right? Because when we do the multiplication, so we do it this way, so there must be the same amount of components. And the result is then a matrix which has got as many rows as we had here, and as many columns as we had here. Right, so that's the core. And then a very simple and straightforward check shows that we have got the associativity of multiplication whenever the multiplication is well defined with the sizes. And we can come to the point and here is the point showing that actually it's never commutative in general, right? So if you multiply these two matrices in the two possible orders, then you get once this one and the other times 0. So there is, as I already told, the associativity of matrix multiplication, and there is the distributivity. And that's really great, right? Because with that we can work, and up to the commutativity of the multiplication, actually the matrix calculus really is more or less the same, just a little bit more difficult than computing with scalars. Right, here is the definition of the inverse matrix. So we just want a matrix which will, by multiplying from left and right in the same time, which will give us the identity matrix, right? So for square matrices, it's okay to request this, but it doesn't work always. Right, and I think this is just enough for this first video, which has introduced. I will always try to summarize in the end. I didn't do it before, but in this video I try to provide guidelines for introduction of the matrix multiplication, to see the absolutely basic properties of this matrix multiplication and addition. It is to see that the matrices, if we restrict to square matrices, they will provide us with something which is called a non-commutative ring. And finally, we also gave some motivation which shows that matrices are useful to take care, and we shall see how useful they are when solving the systems of linear equations.